Right, I'm making an update because I want to show you load testing on here. Now we're at 911 RPM, 160 milliamps. We're driving the motor at the average standard, which is 9 volts, which is driving the rotor assembly. Now I've currently got the output coils connected in series, so we're getting double the actual voltage on the output in AC. So these two coils in the assembly are wired in series right now, and so the wires are coming down. This green wire is looped back to the other coil over there, and the yellow wire and this green wire come down to these clips down here where I had my meters connected before, and the other, now that's the green wire which comes from up here to the other coil, and you see the yellow wire, it goes underneath around the back and it's clipped on the other side over there. Right, so okay, right, so the wires that are coming out the output are coming up here to my full wave. These two white wires actually here. These two white wires are clipped on to the yellow and the green wires here. And these two white wires are AC, coming to my full wave bridge rectifier, which the output is paralleled up with other bridge rectifiers which are not being used right now because they're empty slots. The output comes through the red and white wires all the way along to my boost converter. Oh, my back is killing me. Okay, right, so the boost converter, let's see if I can get some, let me get this light around here, that's better, that's a lot better. I can't see what I'm doing. Okay, the boost converter, at the moment there's nothing on the output connected. Now I'm going to turn my meter on. Right, so having gone through the DC rectifier, the voltage that we have on the output, my flipping mouse is in the way. Right, the voltage that we have, I have to swap hands, hang on. Because I'm casting a shadow. I put my probes on. The voltage that we have, I've got it the wrong way around. Hang on, swap them around. The voltage that we have to the boost converter is only 5.15 volts, but if I disconnect the boost converter, actually we get, let me try and get this in there. We actually now see 11 volts DC, it's climbing a bit. Now, the output current is very, very poor. I've got both coils in series right now. As you can see, it's charging up a little capacitor which is on the rectifier board, and that's how poor the current delivery is right now. It's very, very, very weak. Sorry, I'm losing connections on my probes here. So we're actually seeing about 11.14 volts to the boost converter, which is immediately pulled down when I connect it. When I connect this lead on here, right, and I will go and check the voltage again. There's no load on the boost converter right now, absolutely no load at all. You'll see I'll get this on here, hang on. All we've got really on the input now is 5, oh come on, stupid thing, flipping wires, Trying to get them on. Stay on. I can't seem to get the damn connectors on here. Keeps slipping. I'm trying to do this with one hand. It's difficult. Right, all we've got is 5.18 volts DC on the inputs. The boost converter itself is pulling it down all that amount, so we're not getting a lot of current at all. And when the boost converter is connected without any load on it, apart from the boost converter itself, our RPM is 913, right? And it's dropping. Well, if I take the boost converter off, which has got no load on it, let's look at our RPM. It's going up. So as you can see, we have got a long way to go yet. There's not enough current coming out to actually be of any use to anything at the moment. The RPM is up now up to 931. 932. The input current 150 milliamps, 9 volts, 934 RPM. I am a bit disappointed, obviously, but there's more work to do. There's such a lot of improvements I can still make, and so I'm not just perturbed. But now let's connect this up and see if we can actually do anything useful at all. Right, we've got it connected to the input again. The RPM is dropping, and the current the RPM is going down. Now, basically all we can manage to do is drive this little motor here. Let's just connect this up. I'll try and do this with, hang on, see if I can get this on while I'm connecting it. Right. Oh, I'm blocking the damn view. Okay, the little motor is going around now. So we're able to drive a little motor, and while that little motor is being driven by the boost converter, it runs directly without the boost converter actually, but I wanted to see if I could run the boost converter as well and drive the motor, and it does. But the voltage on the output is supposed to be regulated to about 10.5 volts actually. Let's just measure that. I'll take this off again. I'll put my meter on. The output of the boost converter should be regulated at, well, obviously it's only regulated if it's got enough coming in, enough current coming in. But the actual output is 10.5. Oops, it's come off. Hang on. So we've got 10.5 volts coming out of the boost converter. So that's when it's not under any load. But when I put the motor on it, the output, get it on again, it's come off. I can barely run that motor actually. The output, I've knocked my thing off. The output is actually about 2.6, 2.59, 2.6 volts DC. Which is pitiful. And my little flag thing fell off the motor now, so I've got to stick that back on. It's a bit of, dropped it on the floor now. Hang on a minute, this thing is elusive. Let me just get it back on here. Right. Oh, it's catching on it now. There we go, it's spinning around. Okay, right. So we've obviously not got anything useful right now. We don't have current. We don't have sufficient current. We don't have sufficient voltage, which means it's a fail at the moment. We still have some lensing effects as well. Shorting the coils were reacted differently. It was explained to me by Zero Fossil Fuels. He explained to me what the problem was. We need a proper real power loading, which is what I used with a resistor, 100 ohm resistor. Now that's one way of doing it, but obviously there's another way of doing it, and that's simply by putting an actual physical load on there, which is what I'm doing right now with the motor. And that tells me all I need to know. If it can't actually drive real world devices efficiently, then it's a fail until we actually succeed in overcoming that problem. So yeah, I'm not making outlandish claims. We've got a lot of work, a lot of more development to do, and it costs money, and I must have spent a lot of money on this in the last year alone, and I'm not begging anyone to donate to me. If I can't do it myself, then I'll just give up. If I can't manage to do it, if I don't have the money to do it, then this at some point eventually will just die and become part of the annals of forgotten history. But we'll keep trying as long as we can. As long as we have the ability to finance more materials for the project and develop more new ideas, we'll keep trying to persevere. So anyway, thanks for watching. And in this little extra piece, I'm going to tag on to the end of the other video I just made. We've connected an LED. As you can see, the LED is a 12 volt. This is actually a 12 volt lamp, and it's not even lighting all the LEDs right now. We've got it going through the boost converter right now. I've already tried bypassing it directly to the input, and it's actually dimmer, so it actually benefits from going through the boost converter. The boost step-up converter does actually make the lamp a little bit brighter, but we don't have the amount of current that we need. And now with the lamp connected to the boost converter, our RPM is 906 right now, and the input current is about 160 milliamps. It fluctuates. It's still at 9 volts input. So we're still at 9 volts input, and the actual current input has gone up slightly to about an extra 10 milliamps by the looks of it. Or thereabouts, because that actual power measurement is not, it seems to go up in increments of tens. So it can be on the verge. It was actually on the verge before of 150, 160. And having the lamp on there, it just seems to tip it over that edge to the point where it tricks onto 160, because it was actually fluctuating 150, 160 milliamps previously, whereas now it's a steady 160. Anyway, so we have issues that need to be resolved, which I predominantly believe is due to the coupling on the rotor assembly. Now the rotor assembly, it's the amount of flux that we can actually switch on the actuation, and I've got some pretty large gaps on them right now. I've had to have some pretty big gaps, otherwise the rotors tend to collide with the actual actuators. And I'm actually working on some better coupling techniques to minimize the amount of drag between the rotors and the actuators, which is the concentric assembly. And I'm looking at using a smaller pinprick effect on the actuation, so the magnetic flux could actually be guided more along the iron, but without too much of a footprint, too much of an iron footprint, because iron footprints are the problems that cause drag when you have a large foot. If you have a large foot of iron, that is a huge amount of problem. That's a lot of drag. Having a smaller pinprick where you comes to a point and have a ring on the end, that actually reduces drag. So I'll be looking at those options next, probably. I have some actual pieces of iron that I previously have engineered, cut by the engineering firm. They're in this plastic bag, and it's some pieces of steel with a small taper on the actual end. It's in the plastic bag, so I don't lose it. I've got a few of these lying around, so I'm going to actually try some of these as actuation points between the rotors and the actual concentric points in the middle. So I'm going to see if that actually makes an improvement. That's another phase of testing, which we can be doing. So anyway, enough of that. I'm going to add this on to the other video. Thanks for watching part 2.